Okay, so small addendum to the one that we just did. Let's say that we've got an even simpler circuit. Except this time, what I've got is at time equals 0, we have the charge on the capacitor is going to be equal to Q1, my total charge. In other words, what I'm doing this time is I've completely charged a capacitor, and now I'm going to put it into a circuit and let it discharge and power this resistor for a little while until we run out of power, energy, that's being stored on this capacitor. So we're actually going to look at doing the same thing that we just did, except we're going to look at a discharging capacitor. There isn't a big difference, but there's a subtle thing that you want to keep track of. So here we go. Let me double check this real quick. When I apply loop rule, we're going to have, in this case, I tell you that we've got a total charge Q1. If I apply loop rule, I'm going to have the potential, delta VC, minus delta VR equals 0. I'm going to once again give you R and C as constants. I've also given you that Q1, the total charge on the capacitor, this time as opposed to last time, that's actually going to be a value that I give you. I say that we have a total charge of something, 3 Coulomb or something on our capacitor. All right, as we saw last time, I can now replace delta VC with Q1 divided by the capacitance, C, at least at the beginning. And then, this may actually be an extra step, but that's fine, minus IR equals 0. Give me just a moment. Okay. In this case, this would be, at the very beginning, the total charge that we have on the capacitor at the very beginning, but that is going to decrease. As time goes on, we're going to get the following, that we're going to have some charge on the capacitor of Q, just like we did before. This is the charge at some given time. It is not the total charge, minus our current times our resistance equals 0. The difference here is this is the total charge on the capacitor at the very beginning. In fact, let's make a small adjustment on this. Let's call this one Q0 this time, instead of Q1. So this is what we started with the capacitor with. All right. Now, here's the thing. There's one extra thing that we need to incorporate in this. And when you're discharging, there's actually an extra negative that comes into this. I know I've been absolutely terrible with negatives recently, but in this case, as Q decreases, or I'm sorry, our current, which is going to be equal to, last time we saw that the current equals dq dt. That is still the case, although this time with us discharging instead, we're actually going to have that the current will be equal to negative dq dt. The negative on this is because at this point we actually have a relationship between the charge. Let me rephrase this. When it's discharging, the relationship between our charge on here and the current is actually going to be slightly different than what we saw last time. Last time we had it where the battery was charging the capacitor, and we solved with that. We had an extra term in there. In this case, why we have a negative compared to what we did last time is because last time, as the charge built up on the capacitor, in fact, let me bring up the picture. Oops, that's not the picture. As the charge built up on the capacitor, then it would actually slow down and stop the current. This time we have a negative of that because as the charge leaves the capacitor, that's as it starts dropping down. In other words, this having a high Q, a high charge on it, is actually giving us a lot of current. As this charge goes to 0, our current starts grinding to 0. That is the exact opposite of what we saw when we were charging the capacitor, at which point we had a high current when the charge on the capacitor was 0, and we had a low current when the charge on the capacitor became a large number. For what the work we did last time, the relationship that we used was I is equal to dq dt. In this case, because we have the opposite arrangement, the opposite dependence, we've actually got a negative that we need to introduce. I will go ahead and point that out because it's a common thing to keep track of. When you have positive, or when you're charging, you have one form for the current, and when you are discharging, you're going to end up with the negative. The relationship is switched. There is a different relationship between the Q and the current. All right, so in this case, I need to use negative dq dt. So we've got Q, the charge on the capacitor at some given point, divided by C, minus the current, which is negative, for this case, dq dt, times R equals 0. This is my loop rule. Potential across the capacitor minus the potential across the resistor must equal 0 because that is how I will end up with a closed loop. In this case, the capacitor is charged and it is no longer taking energy from a battery. It is giving energy to the rest of the circuit. That is why it suddenly has switched from a negative to a positive. There are a few things that are subtly different in this circuit than the one we saw before. It is different when you are charging a capacitor than when you are discharging a capacitor. We're going to see similar effects whenever we're dealing with calculus. That being said, I can now distribute this and we end up with Q over C plus dq dt R equals 0. I can subtract this over to the other side and we end up with Q, which is my variable, the charge, over C equals negative dq dt R. I'm going to multiply both sides by C. I'm going to get the following. Q equals negative dq dt times RC. I'm going to do a little bit of algebra all together here, so feel free to double check this, pause and double check. But I should end up with negative dt over RC equals dq over Q. Move the dt and these constants over here, and the negative along with it. Negative 1 is a constant. And I divided both sides by Q, getting me dq over Q. Here is where we once again integrate from 0 to time t, and we're going to go from Q, the initial charge, Q naught, to some lowercase q, like we did in the last one, where that is Q as a function of time. All right, so here we go. On this one, this is nice because I just have Q down here. I don't need to do U substitution. I get the following. I integrate this side and I get negative t over RC equals, well, this is going to be the natural log of little q minus the natural log of Q naught, the initial charge on the capacitor, which happens to be the total charge, at least for this circuit. I can clean this up a little bit, once again using the rules of natural logs. It's helpful to be familiar with those, though as you've seen we keep ending up with kind of the same thing, so it's pretty useful just to be familiar with this. I'm going to take e raised to both sides, and that's going to get rid of this natural log. I end up with this, e raised to the negative t over RC equals Q as a function of time, so the charge on the capacitor at some time t. Remember, we integrated this not for the entire time, but from 0 to some point t. We're going to go from our total charge at the beginning at t equals 0 to some charge Q at time t. So I end up with this, Q is a function of t over my total charge. That was the initial. Finishing this up, I find that Q as a function of t is equal to Q naught, the initial, times e raised to the negative t over RC. I want to show you the difference. The last one, when we were charging, we ended up with this. The total charge, Q final in that case, instead of Q initial, times 1 minus e raised to the negative t over RC. While these seem very similar, they are not the same. One of them is 1 minus the value. In this case, we have just the total charge times e raised to the negative t over RC. But you'll see that you end up with this kind of term showing up each time. That can help you predict what the answers are, because in the last one, I showed you that you could match boundary conditions. We need to do the same thing yet again. So at time equals 0, right when I first connect this circuit, how much charge do we have on the capacitor? Well, at time equals 0, we already know we have Q0, the total. If I plug in t equals 0 into this equation, t equals 0, e raised to the negative 0, well, e raised to 0 is 1, and we do end up with Q of t. So Q of 0, the charge at time equals 0 is in fact the initial charge, Q0. In fact, this is where we get that notation with the naught. We just drop the parentheses. Naught means at time equals 0, and that is why it's the initial. If we look at time goes to infinity, Q of infinity, in other words, we wait a really long time. As t goes to infinity, since this is negative infinity, e raised to the negative infinity, this whole thing goes to 0. 0 times Q0 becomes 0. Our charge goes to 0. If I wait a really long time in this capacitor, this will completely discharge, and the charge on the capacitor will go to 0 after technically an infinite amount of time. All of that then comes down to the RC, the constant, the time constant, where you can actually get approximations, real-life values for that. Though technically, for it to come to a total charge of absolute 0, it would require an infinite amount of time, at least according to what we've got. All right, it does meet boundary conditions. The final thing that I'll talk about with RC, it's called the time constant. We've got the two equations that we've been working with, but real quick, the units, ohm times farad, if you multiply those out, they come up to seconds. It really is a time constant. So let's say, here's where I'm going to start throwing in some numbers. Let's say that we've got a 3 farad capacitor and a 2 ohm resistor. These are kind of ridiculous values. In reality, I should have something like 3 microfarad and a 2000 ohm resistor, but I'm just going to take these numbers and we'll go with them. So we could have microfarads or 3 millifarad and 2000 ohms. That would be far more realistic, but I'm going to keep it kind of simple. My time constant, which we sometimes refer to as tau, is going to be equal to RC, and it will be equal to 2 ohm times 3 farad, which gives me 6 seconds. My time constant is 6 seconds. So here's where I'm going to bring back in one of the equations we looked at. Q of t, the charge on the capacitor as we charge the capacitor, is going to be Q final, times 1 minus e raised to the negative t over RC. If I plug in these values, Q of t is equal to my total charge times 1 minus e raised to the negative t divided by 6 seconds. The charge on the capacitor versus the total charge ends up like this. Q of t equals my total charge times 1 minus, here's where I'm actually going to bring something in, I apologize, not Q of t, Q of 6 seconds. This is the idea behind the time constant. It's a special number for our circuit. Now, it'll change depending on what the capacitance is and the resistance is. It's not always 6 seconds, but it is RC. 3 farad and 2 ohm will give me 6 seconds. Whatever your time constant is, 6 seconds, 10 milliseconds, 1 microsecond, whatever it happens to be, there's something special about that number for your circuit. So if I take at time equals my time constant, 6 seconds, 1 minus e raised to the negative 6 seconds over 6 seconds. Doesn't matter what R and C are, because I would have RC over RC. If tau equals t, then after 1 time constant, 1 tau, if you will, I think is the regular mathematical version, we end up with this. That my Q of 1 tau of one time constant is going to be equal to the total charge times the quantity of 1 minus e raised to the negative 1. Calculator. I'm going to do e raised to the negative 1. I'm going to do 1 minus that. The charge on the capacitor after one time constant is equal to 0.632, roughly, times the total charge. In other words, after one time constant, whatever the total charge is, you end up with 63.2% of the total charge on the capacitor. Here's where the time constant is useful. I made up some stupid numbers to get 6 seconds. Could be any number, because tau is going to be equal to RC. Well, if I put RC in, I have RC divided by RC, it becomes 1, negative 1. Here's where the time constant continues to be useful. After 2 tau, I end up with the following. Not 6 seconds, but 12 seconds, I end up with e raised to the negative 2. Well, e raised to the negative 2, and I do 1 minus that, we end up with the following. We end up with Q times, instead, so if I were to write this out, I'm running out of room here, Q 2 tau is going to be equal to Q1 times 0.865. 2 tau after 2 time constants, in our case, 12 seconds. But twice whatever your time constant is, you end up with 86.5% of the total charge on the capacitor. After 3 tau, 3 time constants, we end up with e raised to the negative 3, 1 minus answer, equals 95.0%. After 3 time constants pass, whatever your time constant is, for our circuit, the random thing that I made up is 6 seconds. So after 18 seconds, 3 tau, 3 times 6 seconds, 95% of my capacitor is charged. I'm up to 95% of the total charge that will end up on that capacitor. Let's do 4 tau. 4 tau is going to be e raised to the negative 4, 1 minus. We end up with 98.2%. By 4 time constants, you have the vast majority of that capacitor charged. Now, the reason that we need this to go to infinity is we will never actually get to 100% until technically this term goes to 0. That's when you'll get 1 times your total value. We do technically need to have time go to infinity. Don't take that to mean that capacitors take literally forever to charge. In real life, by the time you get to 98% or 99.999%, you're pretty much done. As far as you can tell, that last little bit isn't going to make much of a difference, so you don't have to wait an infinite amount of time for your capacitor to charge. Depending on how full you need it to be, you only need a couple multiples of the time constant. In fact, by the time you get to probably 5 or 6 of them, you're going to easily be up in the 99.9% range. I haven't done the numbers. You're welcome to double check. But again, with 6 seconds, we're looking at 24 seconds, half a minute, and we have the thing pretty much fully charged. The value of the resistance does come into play on this. Oops. Yeah, sorry. If you have a stronger resistor, a higher resistance, it will limit the amount of current, which is going to limit how quickly the charge either gets onto the capacitor or off of the capacitor. So R has a factor. And the capacitance, how much is inside, or how much capacitance the capacitor has, also has an effect because it will affect your total charge, I think, among other things. But we can see from the relationship that we do have a dependence on the capacitance. Here's how we can use the time constant and what it represents.